Tonight, we're drifting out to sea, past the bright noise of the shore, into a world where the ocean seems calm, until it isn't. Because sometimes, out in deep water, a wave rises that feels impossible, too tall, too steep, too sudden, a moving wall of water that sailors once called a myth, until instruments began recording the truth. These are the ocean's giants, rare, powerful waves that shouldn't exist, according to simple math. Yet they do. And in the soft darkness of night, we'll explore how they're born, where they hide, and why the sea occasionally breaks its own rules, then quietly returns to stillness. So take a slow breath, and let the sound of water carry you. Out on open water, the ocean rarely behaves like a flat surface. Even on a night that looks quiet from the shore, the sea is doing what it has always done, moving, shifting, answering invisible forces with slow, patient motion. Most of the waves you've ever seen begin with something almost too small to notice. A light wind drifts across the surface, and the water responds with tiny wrinkles, little ripples that catch the breeze the way a raised fabric catches light. Those ripples create more grip for the wind, which transfers more energy into the water, which makes the ripples grow, which gives the wind more to hold on to. It's a gentle feedback loop, like a soft conversation between air and sea. If the wind is steady, the sea organizes. The small, chaotic pattern gradually becomes longer lines that travel together. You can picture it like this. At first, the surface is scribbled with short marks in every direction. But as time passes, certain directions win, and the scribbles stretch into strokes, then into long, traveling bands. The ocean starts to show a preference, an orientation, like it's turning its face toward the wind. And yet, even this organized ocean is not one wave, but many. What we casually call a wave field is really a moving crowd of different waves, each with its own height, its own length, its own timing. Some are short and quick, flicking the surface like nervous fingers. Others are long and slow, lifting the sea as if it's a single enormous chest rising in sleep. One of the most calming things about the ocean, when you're not in danger, is how it carries news from far away. A storm can be thousands of kilometers distant, hidden beyond curvature and cloud and darkness, and still send you its signature. These traveling waves are called swells, and they can cross an entire ocean basin with surprising perseverance. They arrive like visitors who have walked a long road, smoother, more regular, less frantic than the wind-driven waves that birthed them. That smoothness comes from a quiet rule the sea follows. Longer waves tend to travel faster than shorter waves. Over long distances, the fast, long swells pull ahead, and the slower, shorter waves lag behind. The result is a kind of sorting. The ocean becomes less like a messy crowd and more like a procession, lines of water rolling onward, each line spaced with a steady patience. If you've ever watched waves approach a beach and noticed that they come in sets, several larger ones in a row, then a lull, that too is part of the ocean's ordinary breath. Waves of similar lengths can bunch together in groups. The individual wave crests move one way, but the group itself, this envelope of bigger now, smaller now, moves at its own pace. It's one of the reasons the sea feels alive. It doesn't just repeat, it modulates, like music. And beneath all of that, beneath the patterns and sets and swells, there's a mathematical truth that's both simple and endlessly surprising. When waves meet, they overlap. The ocean is not made of separate, politely spaced objects. It's one continuous body of water, and any motion in it shares the same surface. When two wave patterns cross, the surface becomes the sum of both. Where a crest meets a crest, the water rises higher. Where a crest meets a trough, the surface flattens. Most of the time, this adding and subtracting produces something ordinary. It's like many quiet voices in a room. Some phrases align for a moment, but then drift apart again. Because the sea is busy. Wind doesn't blow in perfect lines. Storms rarely stay still. Currents slide beneath the surface, and the shape of the seafloor, even far below, can quietly guide the movement of water above it. So the ocean is always blending wave trains from different origins. A local breeze laying short ripples over the long swell from yesterday's weather. A distant storm sending a deeper pulse. A shifting current slightly changing the timing of what arrives. If you could freeze the ocean and look at it from above with perfect clarity, you might see it as a tapestry of intersecting paths. Some wave trains travel northeast, some west. Some curl around a low-pressure system. Some radiate outward from a storm center like rings from a stone dropped in water. Most of these patterns are not dramatic. They simply exist, quietly sharing the same surface. And when they overlap, they create moments. A moment of unexpected smoothness, when trough meets trough and the surface seems to pause. A moment of sudden steepness, when multiple crests stack. A moment of gentle lift, when a long swell arrives beneath a smaller wave and carries it upward as if on a slow elevator. This is one reason the sea can feel hypnotic. The surface is never truly repeating the same gesture. It is constantly recombining itself, constantly composing and dissolving temporary shapes. To watch it is to watch a living equation, never fully predictable in detail, but deeply patterned in spirit. In the everyday ocean, most waves are manageable because their energies are spread out. The wind has only so much time to push. The fetch, the open stretch of water the wind blows across, may be limited. The wave directions may be scattered, and so the sea stays within a familiar range, a rolling landscape that a skilled mariner can read. But even in this familiar range, the ocean holds the seed of extremes. Because the ocean is a crowd, and crowds do strange things. Imagine standing in a plaza as people flow around you. Most of the time, the movement is smooth. But if a narrow street feeds into the plaza, and a train arrives, and an event ends, and all those separate streams meet, suddenly you can get compression, a pressure point, a dense pocket where motion piles up. The ocean does something similar, not with bodies, but with energy. When multiple wave trains approach the same region with just the right timing, the surface can rise far above its average. Sometimes it's subtle, a wave slightly larger than its neighbors. Sometimes it's noticeable, an unexpectedly tall set. And sometimes, very rarely, it becomes something that feels like a violation, something that seems to step outside the rules of the surrounding sea. The odd thing is that this rule breaking begins with perfectly ordinary ingredients: wind, distance, time, direction, and overlap. Nothing supernatural, nothing added from outside. Just the sea doing what it does, adding and subtracting, breathing in patterns, until, for a moment, a rare alignment occurs. In many places, especially near coasts or shallow shelves, the seafloor shapes the final act. As waves move into shallower water, they slow down. Their energy compresses into shorter distances. They grow taller, Their crests sharpen, their troughs deepen. This is why waves break on beaches, because the front of the wave feels the bottom first, slows down, and the back continues pushing, forcing the wave to tip forward. But far from shore, out where the water is deep and the seafloor is too distant to interfere, the ocean has a different kind of freedom. Waves there can travel long distances without breaking, carrying their energy like a rolling promise. And because deep water allows many wave systems to coexist, it can also set the stage for rare extreme combinations. Sometimes the sea will look almost calm, a few swells, a gentle lift, a dark surface with silver highlights where moonlight touches the crests. And then, without drama, without warning in the human sense, one wave rises higher than it should, higher than the pattern suggests, higher than your mind expects. Not because the ocean is angry, not because it is choosing, but because in a vast moving crowd, there are moments when many separate motions briefly agree. A brief chorus, a brief stacking of the sea's own breath. And then the agreement ends. The surface returns to its usual, rolling complexity. The ocean continues, as if nothing happened. This is where the myths begin. Because if you see that one moment, if you encounter that one wave, you don't experience it as an overlap. You experience it as a wall, a sudden presence, a moving cliff that seems to come from nowhere. For a long time, sailors carried stories like these across centuries. They spoke of solitary waves that towered above the rest, waves that appeared in otherwise ordinary seas, struck ships like battering rams, and vanished. The stories sounded like the kind the ocean invites, exaggerated, fearful, embroidered by memory and night. And for a long time, the world on land didn't fully believe them. It's understandable. The sea is enormous, and human testimony is fragile. Storms are chaotic, and fear can magnify perception. In the absence of measurement, a wave twice as high as the others sounds like a figure of speech. But the ocean doesn't care what sounds reasonable. As instruments spread into offshore regions, oil platforms, wave buoys, research vessels, satellites, something changed. The sea began to write its own witness statements. Data started recording events that matched the old stories. Rare waves far larger than the surrounding field, appearing abruptly with heights that seemed statistically unlikely if you assumed the ocean behaved like a neat bell curve of randomness. These are often called rogue waves. The name fits the feeling. A rogue is not a new species of wave. It's an extreme event within the same ocean. But the experience of it, especially from a ship's deck, can feel like meeting something outside the normal order. Part of what makes rogue waves so unsettling is their contrast. In many accounts, the sea is rough but manageable, and then suddenly, one wave rises much higher than the rest. It can be steep too, taller and more vertical. Not a long, gentle swell you can ride, but a blunt, urgent face of water that demands immediate respect. How can that happen? The simplest explanation returns us to the ocean's basic habit: superposition, the overlapping of wave patterns. If several waves align, their crests arriving at the same place at the same time, the surface height can become the sum of those crests. This is constructive interference. It's the same phenomenon that can make sound suddenly louder when two notes resonate together, or light brighter when waves of light overlap in phase. In a normal sea, with many wave directions and many frequencies, perfect alignment is rare. But rare is not never. especially when you consider how much ocean exists and how often waves overlap across it. The sea has so many opportunities to roll its dice. Sometimes, a wave field becomes more organized. Directions narrow, wave periods cluster, energy concentrates. In those conditions, alignment becomes more likely. The crowd becomes more coordinated, and coordination increases the chance of a moment when many motions add instead of cancel. But rogue waves are not always explained by simple, linear addition. The ocean is not a perfectly linear system. Water has thickness, weight, inertia, and a stubborn relationship with gravity. When waves grow, they can begin to interact in more complex ways, exchanging energy. Under certain conditions, wave trains can become unstable, with energy focusing into a few waves at the expense of others, like a crowd where a few individuals surge forward as the rest fall back. This idea has an eerie elegance. Instead of imagining a rogue wave as a random coincidence, you can imagine it as a kind of self-focusing, a tendency, under the right conditions, for wave energy to clump. The sea, in this sense, doesn't only overlap, it can also amplify. And then there are currents. Currents are rivers within the ocean, broad, persistent flows driven by winds, temperature differences, salinity, and Earth's rotation. Sometimes waves travel with the current, and sometimes they travel against it. When waves travel against a strong current, something important happens. The waves slow down relative to the ground. Their wavelengths shorten. The same energy is forced into less horizontal space. The surface grows steeper. If you want a gentle image, picture a moving walkway at an airport. If you walk with it, your steps cover more ground easily. If you walk against it, your progress slows and your steps bunch closer together. The same stride becomes more compressed. Waves behave similarly when they push against a current. Their stride compresses, making them steeper and more prone to sudden extremes. In places where strong currents meet incoming swells, the sea can become a laboratory for giants. It's not that the current creates energy from nothing. It reorganizes what's already there, squeezing and shaping it. The wave field becomes more intense, more crowded, more likely to produce an outlier. And beyond currents, the ocean has another quiet sculptor: depth. Even in deep water, subtle changes in seafloor topography can bend wave paths, focusing them the way a lens focuses light. A set of waves approaching a region of changing depth can refract, turn slightly, so that energy converges in one area and spreads in another. Most of the time, this effect is gentle. But in combination with other factors, directional alignment, strong winds, currents, focusing can contribute to those rare moments when the sea gathers itself into a single towering shape. It's also worth noting that rogue waves don't always announce themselves as a classic, curling crest. Sometimes the shape is more like a sudden, massive hump, an elevation of water that rises quickly, broad and heavy. Sometimes it's a breaking wave with a vertical face. Sometimes it comes with a deep trough first, a sudden drop that makes the horizon tilt, an unsettling lowering, as if the ocean is inhaling, followed immediately by the towering rise behind it. To the instruments, these are numbers: height, period, steepness, direction. To a person, they are moments of disbelief. One reason rogue waves feel like they appear from nowhere is that our eyes are not good at measuring the sea's true scale, especially at night, especially in rough water, especially when your reference points are moving. A ship rises and falls, your horizon shifts, Darkness flattens depth. A wave that is merely much bigger than the others can feel like a monster because your mind is trying to interpret something that's already difficult to read. And yet, the ocean has produced waves large enough to overwhelm that skepticism. Waves that leave damage consistent with enormous impacts. Waves recorded by sensors. Waves that match the physics of extreme events in chaotic systems. So the modern view of rogue waves holds a kind of quiet compromise. They are not supernatural. They are not guaranteed. They are rare, but they are real. They are the natural consequence of an ocean that contains many moving parts. Wind, currents, wave trains, non-linear interactions, combined in a world large enough for unlikely things to happen with unsettling regularity. If you want to imagine it in a calming way, you can think of the sea as a vast choir. Most of the time, the voices blend into a comfortable harmony, swells and ripples and sets, rising and falling. But once in a while, by chance or by subtle focusing, many voices hit the same note at the same moment. The sound swells, the air vibrates, and the ocean lifts a shoulder higher than it usually does. Then the note passes. The choir returns to its ongoing song, and the sea looks ordinary again, rolling on in the dark, breathing in patterns, carrying its secrets quietly across the surface. When the ocean decides to grow truly large, it often doesn't do it in a single dramatic leap. It builds its giants the way a craftsman builds a cathedral, slowly, layer by layer, with steady pressure applied over distance and time. A storm begins as an argument in the atmosphere. Warm air rises, cooler air sinks, pressure gradients form, and the wind starts to move with purpose. Over the sea, that moving air becomes a hand on the water's surface, pushing and dragging, transferring energy through friction and pressure. At first it looks like nothing, just texture, a dark skin suddenly roughened. Then the texture becomes pattern. Then the pattern becomes structure. One of the quiet keys is persistence. Wind that changes direction every few minutes doesn't build much, but wind that holds its course hour after hour becomes a patient sculptor. It doesn't merely create waves, it selects them. The small chop that can't keep up gets swallowed into the background, while longer waves begin to dominate, stretching their legs across the surface. There's a reason oceanographers pay attention to 3 simple ingredients when predicting wave growth: how strong the wind is, how long it blows, and how much open water it has to work with. That open distance, the uninterrupted stretch of water a wind can blow over, is often called the fetch. A long fetch is like giving the storm a longer runway. With room to accelerate and time to keep pushing, the sea has more chances to absorb energy, and the waves can grow into something grand. But bigger isn't just about height, it's also about rhythm. Storm waves are born messy, many different lengths, many different directions, a chaotic crowd. In the early stages, the sea is a restless field, with short waves scrambling over each other, crests appearing and vanishing, spray rising like white breath. As the storm continues, the wave spectrum shifts. Energy gradually favors longer periods, waves that move more efficiently, that carry momentum with less waste. Out in deep water, waves are dispersive. Different wavelengths travel at different speeds. Longer waves travel faster. Shorter waves lag behind. Over time, this dispersion acts like an invisible sorting mechanism. The sea's motion separates into families. The longer swells march out ahead, becoming smoother and more regular, as they leave the storm's chaos behind. This is why, sometimes, far from any obvious bad weather, you can meet the ghost of a storm. The sky above you may be calm, the wind light, and yet the ocean rolls in long, heavy lines, swells that began days ago under distant clouds. They arrive like a slow message written in water, and they can feel strangely serene even when they're powerful. A swell doesn't always shout, often it simply lifts. In a mature storm, though, the sea near the storm center can become a moving landscape, hills and valleys that never stop shifting. The waves don't come as single creatures. They come as organized disorder, arriving in sets. A few larger waves in a row, then a lull, then another set. To someone trying to rest on a ship, these sets can feel like the storm is breathing in phrases. There's a gentle explanation for that too. Individual crests travel at one speed, but the energy of the wave group, the envelope that makes waves arrive in packets, travels at another. So you can get a pattern where the sea seems to gather itself, then relax, then gather again. It isn't intention. It's simply how wave energy moves through a crowd. And as the storm strengthens, another quality becomes important: steepness. A wave can be tall, but if it has a long wavelength, it may still feel like a broad, rolling hill. When a wave becomes tall and short, when its height grows without enough horizontal length to support it, that's when it begins to look and feel dangerous. The crest sharpens, the face becomes more vertical, the water starts to outrun itself. Breaking often happens when the wave's crest speed can't stay stable. The top begins to pitch forward. Foam erupts, the wave collapses. Near shore, breaking is almost guaranteed because the seafloor slows the wave and forces it upward. In deep storms, breaking can still occur when waves become too steep from wind forcing, from interactions between wave systems, or from currents compressing the surface. And storms don't only create a single pattern of waves, they create multiple, overlapping systems. A hurricane, for example, can generate waves radiating outward in many directions around its center, while an older swell from a previous storm arrives from somewhere else entirely, and local winds lay a rough chop on top of both. The sea becomes layered motion, long swells beneath, short waves above, and everything crossing and combining. This layered sea is where the cathedral can suddenly develop a towering spire. Because when many wave systems overlap, the ocean sometimes focuses its energy. Most of the time, the overlaps smooth out. Crest meets trough, and the surface quiets. But if several crests meet at once, or if wave directions align unusually well, heights can add together for a brief, startling moment. Even without invoking anything mysterious, storms naturally increase the chances of extreme waves simply by creating more energy, more waves, and more opportunities for overlap. There are also places where storms become especially effective builders because the environment helps. Strong currents can reshape storm waves the way a river reshapes a branch floating against it. If waves travel against a strong current, their wavelengths shorten and their faces steepen. The sea can go from rolling to aggressive, not necessarily because the wind increased, but because the moving water beneath changed the geometry of the waves above. And then there are the quiet amplifiers: coastlines, shoals, submarine ridges, and continental shelves. Even far offshore, subtle changes in depth can refract wave energy, bending wave paths so that swells converge in one area and spread out in another, like light through glass. Mariners have long noticed that some capes and banks stand up the sea, making waves steeper and more treacherous. The storm supplies the energy. The geography shapes how that energy expresses itself. Still, it's worth lingering on something calming. Even the most powerful storm waves are not malevolent. They are gravity working to restore balance. The wind adds energy. The water responds by moving. Gravity pulls the surface back down. The sea is constantly trying to flatten itself, and the waves are the visible compromise between the push of wind and the pull of gravity. In that sense, a stormy ocean is not chaos for its own sake. It is physics made large, simple forces amplified by scale. Sometimes those storm-born giants travel far beyond the storm itself. A swell can cross an ocean basin, losing energy slowly as it goes, its lines becoming more regular, its crests spacing out into something almost ceremonial. You might stand on the deck of a ship at night and feel those swells lift you in slow motion. Up, then down, like you're floating on the long, steady exhale of distant weather. And while storms build some of the most dramatic waves humans commonly encounter, there is another kind of ocean giant that follows a different set of rules, one that can be almost invisible in deep water, yet unimaginably powerful. A tsunami is not primarily a wind wave. It does not need a storm. It doesn't need whitecaps or spray or roaring gusts. A tsunami begins when the ocean itself is moved. When a huge volume of water is displaced so quickly that the sea has no choice but to respond. Most often, that displacement comes from the seafloor. Along certain boundaries between tectonic plates, the crust of Earth locks, strains, and stores energy like a bent branch. When it finally slips, sometimes in seconds, it can lift or drop the ocean floor over a vast area. The water above is suddenly pushed up or pulled down. Gravity then tries to restore equilibrium, and in doing so, it sends a wave outward. Undersea landslides can do something similar, shoving water aside as they tumble down slopes. Volcanic eruptions can contribute too, by collapsing or exploding in ways that displace the sea. Even impacts, rare but not impossible, can generate enormous disturbances. The source is different, but the ocean's response is consistent, a large-scale motion that radiates away from the disturbance. The most surprising thing about tsunamis is how they behave in deep water. If you imagine a typical wave, you might picture a crest and a trough close together, like a rolling hill. Wind waves usually have relatively short wavelengths, tens to hundreds of meters. Tsunamis, by contrast, can have wavelengths that stretch for tens or even hundreds of kilometers. That length changes everything. In deep ocean water, a tsunami may be only a meter high, or even less. A ship might ride over it and barely notice because the slope is so gentle. The sea simply rises and falls over a long distance, like the ocean taking a slow, quiet step. But the energy involved can be enormous, because a tsunami moves not just the surface, but much of the water column beneath it. Wind waves mostly involve the upper layers of the ocean. Their motion decreases rapidly with depth. A tsunami, with its vast wavelength, can involve water movement from surface to near the seafloor, depending on depth. It's an entire body motion, not a skin-deep gesture. Tsunamis also travel fast, often as fast as a jetliner in the open ocean, because their speed depends mainly on water depth. In deeper water, they move more quickly. In shallower water, they slow down. This is one of the reasons tsunami warning centers can estimate arrival times across ocean basins. The physics is, in principle, straightforward, even if the real ocean adds complexity. As a tsunami crosses the open sea, it's a quiet traveler. The ocean above it can look almost ordinary. There may be no dramatic crest, no curling lip, no roaring break. Just a subtle swelling that might pass unnoticed without instruments. And then it approaches land, and the rules begin to shift. Near coastlines, the water becomes shallower. The front of the tsunami begins to slow because it interacts with the seafloor. But the back of the wave is still moving faster, still carrying momentum, still arriving with force. The wave compresses. Its wavelength shortens. The energy that was spread across a vast distance becomes concentrated. The sea rises. What was once a gentle slope becomes a steeper surge. This is where the popular image of a wall of water sometimes comes from. But it's important to understand that many tsunamis don't arrive as a single breaking wave. Often they arrive as a powerful flooding surge, like the ocean suddenly deciding to become a fast-moving river. The water can rush inland with relentless force, carrying debris, pulling objects along, changing landscapes in minutes. Sometimes, before the main surge, the sea withdraws. This withdrawal happens if the first part of the tsunami to reach the coast is a trough rather than a crest. The water is pulled outward, and the shoreline can recede dramatically, exposing seabed that is normally hidden. To someone who doesn't understand what's happening, it can look like an eerie gift. Fish flopping on wet sand, boats tilted in mud, the ocean strangely absent. But it's not a gift. It's the ocean inhaling, and when it exhales, it can return with tremendous speed. Another haunting detail is that tsunamis often come in a series. The first wave is not always the largest. The ocean can send multiple surges, spaced minutes apart, sometimes for hours. The coastline doesn't simply get hit once. It can be pressured again and again, like repeated pulses. This happens because the initial disturbance can generate complex wave trains, reflections off seafloor features and continental shelves, and interactions with bays and inlets that can amplify or prolong the motion. Harbors can resonate. Narrow bays can funnel water inward. Some coastal shapes can turn a passing wave into something taller. The way a hallway can make a sound louder by channeling it. In certain places, the incoming surge can reflect back out, collide with the next incoming surge, and build larger local heights, an oceanic conversation of echoes. And still, for all that power, a tsunami is still gravity doing its work. The water is trying to settle back to level after being displaced. The terrifying part is simply how much water was moved, and how quickly, and how the shallows near land force that movement to stand up. Because shallow water does something profound, it takes horizontal motion and turns it into vertical rise and inland flow. The energy can't remain spread out, it has to go somewhere, and so it climbs. In the modern world, we try to listen for these long giants before they arrive. Seismic networks detect earthquakes. Tide gauges measure abnormal sea level changes. Deep ocean pressure sensors, often deployed in buoy systems designed for tsunami detection, can register the faint signature of a tsunami in the open ocean, where human eyes would see nothing unusual. With those measurements, warning centers can estimate wave arrival times and, when data is good, refine forecasts about where the largest surges may occur. But even with technology, the ocean remains a place of uncertainty. Not every earthquake generates a tsunami. Not every tsunami looks the same. Landslide-generated tsunamis can be especially localized and fast, leaving little time to react. And coastal geography can transform a wave in ways that are hard to predict perfectly. So the safest truth is also the simplest. If the sea behaves strangely, if it withdraws suddenly, if the water rises rapidly in an unusual way, if the shoreline changes in minutes, distance is safety. Move inland, move to higher ground, and don't wait for the ocean to explain itself. And now, as we float back into the quieter mood of this journey, you can hold the contrast gently in your mind. There are ocean giants built by wind, storm waves that rise like architecture under the patient hand of weather. And there are ocean giants born from the earth itself, tsunamis that travel quietly across entire basins, almost unseen, until the coastline forces them to reveal their true scale. Both are reminders that the sea is not only a surface, it is a deep body connected to sky, to currents, and even to the shifting crust beneath. And on a calm night, with the world dim and soft, it can be strangely soothing to remember that even the ocean's extremes come from simple forces: wind, gravity, depth, motion, playing out on a planet large enough to make them feel like myths. Far from shore, the ocean can feel like a place without edges, a dark, breathing plain that rolls on forever. And because it looks so vast, it's easy to imagine it as unknowable, something we can only admire from a distance or fear in bad weather. But over the last century, humans have learned a different way of meeting the sea. Not by trying to tame it, not by demanding certainty, but by listening. Listening, in this case, doesn't mean pressing an ear to the water. It means building quiet instruments that can feel what our senses miss. Tiny changes in pressure, subtle rises and falls, the rhythm of waves too long to notice, the steepness of waves too fast to measure by eye. It means turning the ocean's surface into something we can read, gently, like a slow-moving page. One of the simplest listeners is also one of the most faithful: the wave buoy. A wave buoy looks modest from a distance, just a floating shape bobbing in the swells. But inside, it carries a small world of sensors. It measures how it moves, up and down, side to side, tilting and turning. From that motion, it can estimate the height of waves, their periods, and even the directions they're coming from. There's something almost poetic about it, this quiet float, rising and falling, doing what the sea demands, and quietly taking notes. Some buoys are built to measure only the vertical heave, the simple lift and drop. Others are directional, tracking the full motion of the surface, teasing out where the energy is traveling. Some include GPS to measure position changes with delicate precision, and some include accelerometers that feel every jolt, every gentle roll, every sudden slap of water. Over time, these buoys form a network, scattered across coastlines, anchored in offshore regions, placed in shipping lanes and storm corridors. They send data back to land through satellites or radio. And with enough of them, you start to see patterns. Not the pattern of a single wave, the pattern of a living ocean. Because the sea is not just a collection of crests, it is a spectrum of motion, many wavelengths and periods traveling at once. Scientists often describe this with a kind of wave fingerprint, how much energy exists at each frequency and direction. In calmer terms, you can imagine it as the ocean's musical chord. A chord isn't one note, it's a blend. A wave field is similar. It's a blend of rhythms moving across the surface, some fast and sharp, some slow and heavy. And when you record that chord over time, you can hear the sea change. You can watch the swell from a distant storm arrive hours before the wind shifts locally. You can see a storm build, not just in height, but in the way the wave periods lengthen. You can watch the ocean sort itself, shorter waves fading, longer swells dominating. You can also catch the rare moments when the ocean does something unusual. Not unusual in a mystical sense, unusual in the statistical sense. A sudden spike in height, a wave much larger than its neighbors, a steepness that rises beyond what the surrounding conditions would lead you to expect. Sometimes these moments are fleeting. One wave, then the sea returns to its previous rhythm. But because the buoy never blinks, it notices. Offshore platforms have also become listeners in their own way. Fixed structures in the sea, oil and gas platforms, research towers, wind turbine foundations, often carry sensors that measure the force of wave impacts and the elevation of the sea surface around them. While buoys drift and bob, these structures stand still, which gives them a different kind of relationship with waves. They can record the way a wave hits, a shove, a slam, a vibrating roar through steel and concrete. For engineers, that data is invaluable. It tells them not only how high the sea was, but how it behaved when it arrived. A tall wave that is long and smooth pushes differently than a tall wave that is steep and breaking. One is a heavy lift, the other is a hammer, and the ocean, depending on conditions, can be either. Then there is the quiet perspective from above. Satellites pass over the sea in wide arcs, looking down with instruments that don't care whether it's day or night. Some satellites measure the ocean's surface height using radar altimeters, sending pulses down and timing their return. From that, they estimate wave heights across broad areas. Others use radar imaging techniques that can reveal the texture and direction of wave patterns, like seeing the grain of the sea. What satellites offer is context. A buoy tells you what happened in one place. A satellite can hint at what is happening everywhere. How large swells radiate outward. How storms imprint their patterns across basins. How currents shape the surface in subtle ways. It's the difference between hearing one instrument and hearing the whole orchestra. Closer to the surface, there are coastal radars that watch the sea from land. Some radar systems can map surface currents and wave conditions over wide stretches of coastline. Harbors and ports often use these observations because the difference between a safe approach and a dangerous one can be a change in wave direction, a shift in period, a small rise in swell height. And on ships themselves, especially larger vessels crossing open water, there are onboard weather instruments, wave radars, and constant streams of forecast updates. A modern ship is not blindly wandering into the unknown. It is, in many cases, navigating through a moving forecast, adjusting course and speed, like a traveler choosing a calmer road. All of this observation creates a new kind of ocean knowledge. But observation alone is like taking notes without understanding the story. So the next part of listening is modeling, building mathematical stories about how waves are born, how they travel, how they change. These models don't predict the exact shape of every crest, because the ocean is too complex and too sensitive for that. Instead, they predict the overall behavior, wave height distributions, dominant periods, directions, the evolution of swell fields across time. In gentle terms, a wave model is like a weather forecast for the water's motion. It begins with wind, because wind is the main sculptor of ordinary waves. The model takes wind fields from atmospheric forecasts and calculates how energy transfers into the sea surface. It tracks how wave energy grows under sustained wind, how it disperses as it travels away from storms, how it interacts with currents, how it refracts over changes in depth, how it loses energy through braking and friction. Instead of thinking in single waves, these models think in spectra. How much wave energy exists at different wavelengths and directions. Over time, the model moves that energy across the ocean, allowing swells to travel, combine, and decay. Even without naming any specific software, you can imagine the ocean forecast as a living map. Arrows show swell directions, colors show wave heights, numbers show periods. You can watch a storm in the Southern Ocean generate long swells that march northward. You can watch a hurricane send energetic waves outward like a pulse. You can watch swell systems cross and overlap. And when swell systems overlap, the forecast becomes more than just height. It becomes sea, state, how confused the waves are, how many directions are present, whether the ocean is orderly or crosshatched. This is important because some of the sea's most uncomfortable and risky conditions aren't simply big waves, but waves coming from multiple directions at once. A ship might handle a large, orderly swell better than a smaller, chaotic cross sea, where the motion becomes unpredictable. In this way, forecasting is also a kind of translation. It takes an ocean that feels like a mood, calm, choppy, heavy, uneasy, and turns it into measured descriptions that can guide decisions. But the ocean still has its rare giants, the ones that appear suddenly, or the ones that carry energy in hidden ways. So part of modern listening involves estimating extremes. Engineers and oceanographers ask questions that sound simple, but have deep consequences. How often might a wave above a certain height occur? How likely is a truly steep wave in this region? What is the worst reasonable sea state a structure might face over its lifetime? These are questions of probability, not certainty. The ocean doesn't promise it will be polite, but it also doesn't break rules casually. Rare events are rare. The challenge is to estimate them well enough that ships, platforms, and coastal defenses can be built with appropriate caution. This is where concepts like significant wave height enter, an idea used to describe the general sea state in a useful way. It's not the highest wave, it's more like a representative value tied to the larger waves in a given period of observation. From that, one can estimate the likely range of individual wave heights, because individual waves can be higher than the significant height, sometimes much higher. Even in gentle seas, there are always outliers. The ocean is a crowd, and crowds have occasional surprises. In more advanced approaches, forecasters and researchers look for conditions that increase the probability of rogue waves, strong winds creating energetic seas, currents opposing wave directions, wave energy concentrated into narrow directional bands, the presence of crossing swell systems, or regions where wave focusing might occur due to current gradients or depth changes. The ocean, in other words, has neighborhoods where extremes are more likely. And the goal is not to predict the exact rogue wave, because that may remain beyond our reach in most cases, but to identify when the sea is entering a regime where the risk rises. A bit like weather forecasting that can't tell you which exact street will see the biggest gust. but can tell you when a storm front is arriving and conditions are becoming hazardous. In recent years, researchers have also explored real-time detection aboard ships and platforms, systems that analyze incoming wave measurements and look for abnormal steepness patterns or unusual group behavior. Some shipborne radars can estimate wave fields ahead, providing a kind of short-range nowcast. It's not a guarantee of safety, but it's another layer of listening, another soft warning that the sea might be about to do something sharp. When it comes to tsunamis, the long giants, the listening becomes even more urgent and even more quiet. Because a tsunami in the deep ocean can be nearly invisible. So the world relies on networks that detect the sources and signatures of tsunamis. Seismic stations monitor earthquakes, estimating their magnitude and location quickly. But magnitude alone is not enough. Some large earthquakes don't produce major tsunamis, and some complex events can produce more sea displacement than expected. So there are also instruments in the ocean itself. Deep ocean pressure sensors that detect tiny changes in the weight of water above them. Changes caused by a tsunami passing overhead. These sensors can transmit data to buoys and satellites, sending quiet alerts across the world. Along coastlines, tide gauges and sea level stations watch for unusual surges. When a tsunami is detected early, warnings can be issued with precious minutes or hours of lead time, depending on distance. The ocean's long wave travels fast, but the world's communication can travel faster. Sirens can sound. Emergency messages can reach phones. Evacuation routes can fill with people moving inland and upward. And yet, even with all this, the sea remains complex near the shore. The shape of coastlines and sea floors can amplify or reduce wave heights dramatically from one bay to the next. So warning systems often speak in probabilities and expected ranges, updating as real measurements arrive. The listening continues in real time. Pressure sensors, tide gauges, and coastal observations refining the picture as the event unfolds. If all of this sounds like a lot of machinery, buoys and satellites and models, it can help to remember the simplest reason it exists. Because humans build lives around the sea. We fish, we trade, we travel, we build energy infrastructure, we sail for work and for wonder. And so we need a relationship with the ocean that includes both awe and practical respect. That respect shows up in design. Ships are shaped with the sea in mind. Their hulls are designed not only to float, but to endure repeated stress. Engineers think about slamming forces when a bow meets a steep wave, about fatigue when waves flex a structure thousands of times over months, about stability in cross seas, about freeboard and how waves wash over decks, about the way a ship can be vulnerable when a wave hits at the wrong angle. Offshore structures are designed with return periods in mind, how strong a storm might be over decades, what wave heights could plausibly occur, how to survive impacts without catastrophic failure. Wind turbines at sea must handle both wind loads and wave loads, often simultaneously, their foundations enduring a constant dialogue between air and water. Coastal defenses, too, are built with listening. Seawalls, breakwaters, dunes, and engineered reefs are designed to reduce wave energy before it reaches vulnerable places. In some regions, nature itself is part of the design. Mangroves, salt marshes, coral reefs, living structures that soften waves and reduce storm surge impacts. And the forecasts feed daily decisions. A cargo ship chooses a route that avoids the worst seas, saving fuel and reducing risk. A fishing crew decides whether the swell period is safe for launching. A port authority determines whether conditions allow safe docking. A coastal town watches storm surge forecasts and tide cycles. A rescue team times operations with wave sets. The ocean becomes something you can't control, but can understand well enough to move with it. Still, even with all this listening, the sea keeps a certain kind of secrecy, because measurement has limits. A buoy records the sea where it floats, but the ocean is wide. Satellites pass overhead, but not constantly. Models approximate reality, but reality has details too fine to capture fully. Currents shift, storms evolve. Non-linear wave interactions can create outcomes that are hard to foresee in exact form. And there is something else that resists prediction: the precise timing of alignment. A rogue wave, in many cases, is the product of many small factors lining up. If you shift any one factor slightly, the phase of one wave train, the direction of a wind gust, the local current speed, the extreme wave might not happen, or might happen somewhere else, or might be smaller. So the ocean retains its right to surprise us. But perhaps that is not a failure of science. Perhaps it is simply the ocean's scale showing itself. When a system is vast and energetic, rare events are part of its nature. The goal is not to eliminate surprise, but to reduce vulnerability, to build with humility, to forecast with care, to prepare communities, to train crews, to respect warnings, and to remember that the sea is never obligated to match our expectations. There is a quiet comfort in that, if you let it be gentle. Because listening changes your relationship with the unknown. Instead of imagining the ocean as pure unpredictability, you begin to see it as a place with patterns. Complex, yes, but real. A place that speaks through rhythm and pressure and wind fields and long traveling swells. A place that can be studied without being diminished. And on nights like this, when we're floating through the idea of the sea rather than fighting through it, listening becomes almost meditative. You can imagine the buoy rising and falling, patient and steady, like a slow heartbeat. You can imagine the satellite passing overhead, scanning the dark surface with invisible pulses. You can imagine the wave model tracing lines across the map, like a calm hand sketching the paths of swells. You can imagine, too, the human side. Someone in a quiet room watching the data update, noticing a shift, issuing a warning, or simply observing the sea's ongoing conversation with the sky. The ocean is always moving, and so our listening is never finished. We collect data, we refine models, we learn from storms, we rebuild after disasters, we improve sensors, we train people to recognize danger signs, like unusual sea withdrawal, rapid water rise, or unexpected wave steepness. We share knowledge across countries because the ocean connects everything it touches. And still, the sea will occasionally lift itself into a giant, a steep, sudden wave that feels like a myth made real, a long, quiet tsunami that carries the motion of the earth beneath, a storm swell that arrives from beyond the horizon, heavy and steady, like the ocean remembering weather from days ago. When that happens, we don't truly beat the ocean. We do what sailors have always done at their best. We notice, we respect, we adjust. And when the sea calms again, as it often does, we return to that softer truth. Most of the time, the ocean is not trying to harm anyone. It is simply being what it is, a deep, moving body on a living planet, translating wind and gravity into rolling forms. So as you rest, you can let that thought settle. Somewhere out there, across the dark water, instruments are listening, quietly keeping watch, while the ocean continues its slow, endless breath.